Okay, so welcome back. This is our fourth video about the lecture of modeling Bayesian networks. And in this video, we're going to touch a topic that is slightly different from the previous ones. We're going to discuss how to deal with large CPTs. So in some cases, we have variables that have a large number of parents. And we know that the size of the CPT will grow exponentially as we increase the number of parents. So in this table here, we have the number of parameters growing in an exponential way with the number of parents that we have in the node. And even for when the number of parents is not that large, for instance, we have 10 parents. It's not difficult to imagine that we can have a correlation between one variable and the other 10, so we can have like a disease and 10 different possible symptoms. The number of parameters that are going to be the number of probabilities that we need to list or to find from data is quite large. It's like 1024 for just 10 parents. And this considering binary variables, that is an optimistic case. So the problem here is that we have two phases, right? So we have the modeling issue and we have the computational issue. The modeling issue tends to appear first because when we are creating the Bayesian network, then I'm going to try to fill in the tables with numbers. We'll have to some way to find out these 1,000 different probabilities for 1,000 possible combinations of those variables. And in the case that those probabilities will be listed from an expert, it's going to be very difficult, right? So to list all possible, for instance, combinations of symptoms for a disease, and expect that the person will be able to accurately estimate what's going to be the probability. There is also the computational problem, but that computational problem tends to occur for even larger number of parents. That is the exponential growth of the tables. And in this case, if you imagine for 10, is already a problem for modeling because it's already difficult to elicit these 1,000 probabilities, but it's not difficult to store 1,000 probabilities or even compute anything that we want to compute for 1,000 entries. So the computational problem will appear, but for a much larger number of parents. So it's going to happen when we have like a 20 or 30 parents. At this point, we will feel that the inference starts to become slow. So there are a few techniques that we can use that will help us to model those large CPTs in an efficient way. Of course, we have to make a few assumptions in order to use those models, but in some cases, those assumptions are reasonable and will lead to, I would say, good approximations of the real world. So let's take a look on that. So probably the most famous of all those models is called the noise OR. And it's a sort of what we call micro model. And the idea is very simple. So we can take the causal interpretation in order to make it a little bit clear. But imagine that we have a common effect, that is E, here on the bottom. And we have several possible causes that are calling C1, C2, until Cn. So the causes are my parent nodes here on the top, and the effect is my node variable. And we assume that this n is large, so we need to make an approximation for that in order not to have this exponential size conditional table inside the node C. So we think that each of these causes, C1, C2, until Cn, is capable of establishing the effect by its own. So if you look here at the circuit, we have this OR gate here, right? That's taking as input the output of all these possible causes. There is one exception, right? So under some unusual circumstances, there is one suppressor variable, Pi, that is going to eliminate the effect of each of the causes. So we have one variable here, key1, key2, associated to each of the possible causes, and if this variable is activated, so you're going to suppress the cause and not allow that to activate the effect. And we have one final variable here that we call the leak variable, and it has a meaning sort of represent all the possible causes for E. So just to make a very simple example, maybe it's not the best example because it doesn't match exactly this causal interpretation, but we can think about a disease that's very common, has different symptoms, that is flu. For instance, we can say that one symptom for flu is fever, and the other one is sore throat, and the other one is headache, and so on. I know that is not the perfect example because when you think about the causal interpretation, we usually think that the disease is causing the symptoms and not the symptoms cause the disease. But yeah, I think that you're gonna understand the example. So in the noise or model, what we say is that one of those causes will be enough to activate the effect. So basically saying that if the person has fever, or if it has a sore throat, or if it has a headache, it will be enough to diagnose that person with flu. Unless we have this suppressor variable, that they usually have a very small probability, like 5%, right? So if this variable key1, for instance, is activated, it will cancel C1 and the person will not have flu. So we can say that we expect that a small percentage of everyone that have fever do not have flu, so we will model with the suppressor variable. And finally, we have a leak variable that here on the bottom that goes directly to the OR gate. And this leak variable is gonna in some way summarize all other causes that are associated with flu that are not modeled into C1 to Cn. So we can expect that there is also possibly a small number of people, I don't know, like 2%, that they have flu, but they don't have any of those symptoms. The noise or model can be modeled with a very small number of parameters. So we just need n plus 1 parameters to specify the CPT. So what we will need? We will need the probability of each suppressor variable to be active, and also the probability for the leak variable to be active. So now we need to compute the probability for one specific entry of the conditional probability table. So let's suppose that we have 5 parents, and we are interested in this instantiation here. So the first parent will be active, the second will be active, the third is going to be passive, the fourth is going to be passive, and the 51 is going to be active. So we'll call this instantiation here alpha, and we'll call I alpha the indexes of these parents. So in this case, the index of the active parents. So in this case, the active parents are 1, 2, and 5, right? So to compute the final probability for this model, and this probability is this one here, is going to be the probability of this output E to be passive given the alpha that is instantiation. So to E to be passive, we cannot have the leak variable, and also we need the suppressor variables to be active for each of the active causes. So first term here is what is the probability of the leak variable to be passive. So it's going to be 1 minus this probability here, that is the probability of the leak variable to be active. And we need to multiply, and I see that here we are assuming that all the suppressor variables are independent, we're going to multiply the probability of each suppressor variable to be active. And this is going to occur for all the causes that are active. So I'm going to look for the cause, in this case 1, 2, and 5. So these are the ones that might activate my output E. So it's going to be 1, 2, and let's suppose this one is 5. And I needed that to be suppressed. So I needed this guy here, and this guy here to be active. So we have these probabilities here, and I will multiply them. Okay, and just to make things a little bit more concrete, let's look at one example. So if we look back, we have this example of a medical diagnosis problem where we had several symptoms and diseases. And for instance, this is part of our Bayesian network. We have sore throat as being a symptom for 3 different diseases like cold, flu, and tonsillitis. And let's suppose that, okay, this is not a very big one. We should expect a lot of more parents in order to use a nose OR, but let's suppose that we want to use the nose OR for this CPT. And in this case, we have to specify what's going to be the leak probability. Let's suppose that we stipulate it's going to be 0.02, and also the suppressor probabilities for the variables C, that's cold, F, that's flu, and T, that is tonsillitis. And in this case is 0.15, 0.1, and 0.05. So what's going to happen here is that for each entry that we have here in the conditional probability table, I can compute one probability. And we're going to use the equation that I showed to you in the previous slide. So in this example here, just to instantiate here, we have cold, we have flu, we have tonsillitis, and here S is going to be sore throat. And well, we're going to compute the probability of having a sore throat. So here sore throat is going to be true, right? That's why it's appear 1 minus here in all those entries of the table, is because I computed the probability of having a sore throat given the other conditions. So in the case that the person has all the symptoms, it has cold, it has flu, it has tonsillitis, so this is going to be the probability of S is high. And the probability of S being high is 1 minus the probability of S being low. So this is the probability of S being low that we saw in the previous equation. It's going to be, first term here is the probability of not having the leak variable active plus times the probability of having the suppressor variable for each cause. So I need all suppressors to be active. So as we expected, this multiplication of all those small numbers here is going to be a very small number. So this number here, that's 1 minus this small number, is going to be a large number. So it means that the probability of a person having the disease, given all the symptoms, is going to be very high. And as we eliminated the symptoms, so now the person has no tonsillitis, here the person has no flu, and here the person has no cold and no flu, no tonsillitis. So we see that these probabilities tend to go down. So maybe it's not a perfect model for this problem, but we can see that it is in some way an approximation for what we expect. So more symptoms seems to be a stronger evidence that the person has a disease. So as the person has more symptoms, the probability tends to increase. So this is the noise OR. Of course, is not the solution for everything. Several problems do not follow this model, right? So we cannot expect that all causes will be potentially capable of activating the effect. So we need some other additional model. So let's take a look at other variations, but this noise OR model is very, very common, very well known. So this is one example that we can see that there is some structure here, but it doesn't fit the noise OR model. So for instance, we have this table. We are just showing the probability of the output to be 1. And we can see that for variable C1, when it's 1, the probability is 0. So it doesn't fit the noise OR model. For all the other variables, like when C2 is 1, the probability is 0.9, and it is independent of C3 because C3 can be 1 or 0 here. It doesn't change. So we see that there is structure, but it's not what we expected with the noise OR. So we needed to use something else, something different, and let's see a few possibilities. So one possibility that's very simple to understand and also to implement is called the decision tree, or variations that we call decision graph. So trees have no cycles, and graphs can have cycles. So a very simple example here for the previous slide is this decision tree. So basically the decision tree is going to be a sequence of tests. In each test we look at a different node and branch the tree, and we expect that by dividing the space we're going to be able to isolate the case of a certain values of probabilities and use this as a model. So in this case, C1 is our first test, and it can have two different values. It's 0 or 1. If C1 is 0, so the probability of E equal 1 is going to be 0. And that's solved. So we isolate several rows of the table in a single test, and that's good. So you're going to save space for representation. If C1 is 1, we cannot decide yet, so we're going to look at C2 and see what's the value of C2. If C2 is 0, we can conclude that the probability of E equal 1 is going to be 0.9. Otherwise, we have to test for C3 and so on. So we can see here that if we have a lot of structure in the table as we had in the previous slide, so we can use a small number of variables, right? A small number of tests, and the structure will be linear in the number of parents. But it's a sort of an optimal case, right? If we don't have a structure, so in this case, we're going to test and test and test again, and this structure will grow, and it may have exponential size in the number of parents, so you will not save any space here. So it's very important to have some form of structure in order to use this representation. A very similar representation is if-then rules, and in this case, we model the CPT using tests, and these tests are propositional sentences using the parent variables of the node. So the test has this form here. It is if the sentence alpha I is true, then we conclude that the probability for the CPT is Py. So for that example, we know that if C1 is 1, we can conclude that the probability of E equal 1 is going to be 0. Okay, so I see now zero mistakes here, 0.0, 0.9, 0.3, 0.6, and 0.8, the correct number. Sorry about that. And if C1 is not 1, right? So if C1 is false, I need to check for something else. In this case, it's going to be C2. So if C1 is false and C2 is true, so I can conclude that the probability of E equal 1 is going to be 0.9. And I keep doing that. So what we can see here that we are taking a little bit of care. We are making this alpha I sentence mutually exclusive. So what we are doing is that we are not allowing two rules to fire at the same time. So if we have this case here, okay, if C1 is 1, we fire the second rule. Notice that we fire the first rule. Notice that the second rule is only fired if the first one is not fired, because the first test here is C1 equal 0, right? So they cannot be be fired at the same time. They also exhaustive, so it means that they're going to cover the entire space, and we will have one probability associated for each possible instantiation of the parents and the node variable. So they're going to cover the entire space, right? That's also very important because in this representation, we cannot have probabilities for some instantiations that do not have a probability for the other instantiation. We need to have probabilities for all possible instantiations. So it's very important that these premises, right, the sentence alpha I, to be mutually exclusive and also exhaustive. So again, this representation can be very efficient. It's pretty much very similar to the decision trees, but it translated into rules. But they can also be exponential if the CPT, the conditional probability table, lacks a bit of structure. And when we have deterministic CPTs, that are those CPTs that only have 1 and 0 probabilities, what we can do is to use propositional sentence to represent the CPTs. And it's very simple to do. We have here one example, and if it just 2 propositional sentence, we can summarize this entire table here that we use in one of our modeling examples. So what is saying here? It's saying the following. Well, if the gate is working okay, so just you to remind, we have this case here where we have a gate X is an inverter gate. We have A as input, C is going to be the output, right? So we expect that C is going to be the negation of A if the gate is working okay. So if the gate is okay and A is high, so we expect C to be low. That's okay. Or we have a stuck at 0. That is one problem where the gate stays in 0, it does not change. So these 2 conditions here will be enough to imply that C is low. But look at that, we have here equivalence, because it's also true that if C is low, we expect it to have the following: or the gate is working okay and A is high, or it is stuck at 0, right? So these summarize the cases. The other case is for the C is high. And when C is high, we can expect that the gate is okay and A is low, so the input is low, or we are stuck at 1. So we have the fact, and the gate is at a high level, it doesn't change the output, right? And it's also true in the opposite direction, that when we have X okay, so the gate's okay and A is low, or we are stuck at 1, we can imply that C is going to be high. So this is a very compact representation for a table. We understand that table is not very large, but if we have several parents, we could summarize the entire table in a few rules if the CPTs are deterministic. Okay, so we got to the end of this lecture. It was a very long lecture because chapter 5, in which this lecture is based on, from the textbook, it's a very long chapter. So I invite you to take a look on this chapter. I think that's very interesting, and you see that the book covers some other models that we didn't cover. We didn't cover because we don't have time for covering all of them, and not because these ones that we cover are the most important ones. I guess the other ones that are there are also some good examples. I selected those ones because they are simple and they illustrate different types of queries, different type of analysis, and different modeling techniques. We also cover different representations for large CPTs, and I guess those representations, initially they solve what we call a modeling problem, so we don't have to list a large number of probabilities, but they also can help to solve a computational problem. For most of the algorithms that we're going to see, you see that we need to expand that table we need to expand that representation to the complete table in order to make the inference. But there are a few algorithms that can use the compact representation. Okay, and in the next lecture, we're going to start discussing how we can use Bayesian networks to do the classification task that's very popular in machine learning. See you.